All right, welcome everyone to my pre-class video for the cylindrical and spherical surfaces. And before we do any cylindrical or spherical stuff, there's another type of problem that's introduced in in this section, and it's continued on in the next section when we parameterize surfaces with arbitrary parameterizations. So there's another type of problem where it wants you to be able to find a normal vector uh, on a surface at a particular point. And then we can also use this actually in the next section, we'll be finding tangent planes. And so before we get into the cylindrical and spherical, I think that this is a very interesting topic in its own right, and it's fairly complicated. So I think it's worthwhile to see this maybe multiple times. And so before we even get into the cylindrical spherical stuff, I thought a good focus for this video here would just be how do you find a normal vector for a surface at a particular point? And then how could we, of course, use that to find a tangent plane? And so first thing, we're going to be doing this problem on this surface here. It's 7 minus x squared minus 2y squared. And so this is what it looks like. It's kind of one of these paraboloid sort of deals. And we're going to be interested at this point 1, 1. So I have this point plotted here. And this is very nice. You can go ahead and do a few things. For instance, if I do this drop-down menu right here, you can see that I can show the normal vector at this point. So this right here is the normal vector. It's a vector, if you were to zoom way in on this, right, it would be at a 90-degree angle with the surface. So it kind of sticks directly out, kind of away from this surface. So that's what the normal vector looks like. And our goal is to be able to find this normal vector. And of course, if you change the points, so we can see if I change the x, for instance, this kind of changes. Oops, I had a kind of a bad view here. Let me do it here. So if I change the x value like this, of course, the normal value changes, or the normal vector changes, as you would probably guess. And likewise, if we change the y, maybe now I need this view. This also changes, right? And this is kind of nifty. You can just take this point and drag it around and kind of see what the normal vector looks like. So, I mean, it's fun and everything. But the question is, how do we go about finding this? So this is what we need to discuss. And I guess the other thing, like I said, is we can use this then to find a tangent plane, right? Because once you have a normal vector, you can find a plane with that given normal vector. And I just wanted to show you kind of what this looks like as well. So instead of the normal vector here, where is it? Show the tangent plane at this point. So if I click on this, so there is the tangent plane. And again, if we kind of move this around here, I have two things moving. That's probably not good. Stay still graph. There we go. So if we kind of move this point around, you can see that it's, again, kind of completely flat. Instead of tangent lines, now we're doing kind of three-dimensional stuff, there's going to be a plane that's kind of nice and flat with surfaces like this. So we're going to maybe find this tangent plane, again, by using that good normal vector. All right, so that's what I thought would be a interesting idea to go over in this pre-class video. I'll give a go at my explanation and everything, and we'll do some calculations. So I need to switch over here to my iPad. So let me go ahead and share screen with my iPad. Pull this up. Take a drink of water while it's doing this. And here we are. Find the normal vector to this surface at the point 1, 1. And so again, kind of we have this sort of paraboloid sort of deal. Looks something like this. And we want to find the normal vector at this point 1, 1. So just kind of give an idea, remember what this looks like. And again, this is supposed to kind of stick up out of the page. It's supposed to be at a nice kind of 90-degree angle with the surface there. So that is our goal. What we're going to do for this is that we're going to actually use some curves, right? And we're going to find tangent curves or tangent lines or tangent vectors for those curves. And then we're going to go ahead and take the cross product, and that's going to help us get this normal vector. So, okay, that sounds a little bit complicated, but it's really not so bad. So maybe the first thing that I want to do, I'll draw a little coordinate system here. So here's the z, here's the x, and here's the y. X, Y, Z. is that I'm going to go ahead, and again, I have this nice surface and everything. We just came from, chapter 13 deals a lot with space curves, and we want to utilize all those skills. So for the time being, I'm going to go ahead and fix y, right? So of course, we're very interested at 1, 1. And so if I'm going to fix y to any particular point, let's go ahead and fix y to 1. So I'm going to choose y is equal to 1. And then we can see that when we do this, if I hold y to be equal to 1 here, this surface, kind of if I choose all the places where y is equal to 1, it starts to look a lot like one of these space curves, right? So these are all the places where y has a value of 1. And so we could think about parametrizing this curve. And of course, the way that we would do this is that notice that x still can roam free. X is not fixed in this case. It's just y that's being fixed. And so you could think about the parameterization r of x, and we can switch these to t's here in just a second. But x, again, can be whatever it likes. Y is going to be fixed at 1, right? And then z is going to be given by this equation here. It's going to be 7 minus x squared. And then minus, well, 2 times 1 squared is just going to be minus 2. And so again, if we would like this in terms of t for our parameter, that's perfectly fine. We can do that. And this is going to be t1 and 5 minus t squared. And then from 13.2, we remember a direction vector, right? If you're very interested in a direction vector, what you can do is that you can take the derivative of this. So I'm going to go ahead and take the derivative of this. And in that case, I get 1, 0, negative 2t. And now, of course, right, this is going to give us this direction vector kind of all along this line here. Now we need to go ahead and let it know that we're also interested when x is equal to 1. And again, I swapped out my x's. Instead of x's, I have t's here. So I'm going to go ahead and figure out this direction vector at t equals 1 or x equals 1. And we're going to get 1, 0, negative 2. So, okay, what have we accomplished here? What this is saying is that if we were to zoom in on this here, and I was standing at this point, right, the direction vector would be 1 in the x direction. So again, remember x is coming out of the page. So 1 is coming out of the page. We're not moving at all in the y direction, which makes a lot of sense because y is fixed. And we need to move 2 down. Z equals, right, negative 2. So again, 1 in the x direction, none in the y direction, down 2 in the z direction. And hopefully this is a nice perfect tangent vector here. So again, 1 in the x, 0 in the y, negative 2 in the z. So it should look something like this. So we have now 1 tangent vector. Again, we're hoping for 2 tangent vectors. Then we're going to take the cross product, because the cross product gives us, this vector that's going to be perpendicular or normal or orthogonal, whatever your favorite word is, right? It's going to be orthogonal to these other 2 vectors. So that's going to be our goal. So just like we just did this, and to get 1 tangent vector, you could say, well, why did you hold y constant? Why not hold x constant? And that's going to be the key to getting our second tangent vector. So now instead of holding y constant, we're going to go ahead and hold x constant. So we kind of need to reset our thinking completely, hit the refresh button. And so if I hit, if I hold x to be equal to 1, so again, kind of we take a step out by 1 here, we're going to get, again, kind of a parabola sort of deal, again, where all the places where x is equal to 1, probably going to look something like this. Now y is not being restricted at all. It's only the x that's going to be restricted. And so in the, the algebra, the equation, when I actually go to, start plugging these things in, well, x is equal to 1. So if I want maybe r of y, again, kind of my y is still a variable. It's allowed to be whatever it wants sort of deal, but x is going to be equal to 1. So if I wanted to parameterize this curve here, this green curve that I just drew, we would have, well, again, x is equal to 1. Y can be whatever it wants. And z is going to be, again, from this equation right here, but I went ahead and I fixed x to be equal to 1. So if I go ahead and subtract away 1 squared, I'm going to get 6 minus 2y squared. And again, most of the time in 13.2, we dealt with when this was a parameter t, right? Our variable was usually t. So if you'd like to, you can go ahead and swap this all out and make these t's instead of y's, just so that way it's consistent with what we've been doing before. And then if you want a directional vector, as we did in 13.2, well, that means you want to take the derivative. So if I take the derivative of this, I'm going to get, well, the derivative of 1 is 0, the derivative of t is 1, and the derivative of this is going to be negative 4t. And, well, now we need to tell it, right, that not only should x be equal to 1, but I'm interested in the directional vector when y is equal to 1 as well. So let me go ahead and plug in the y value, which again, we've substituted y for t instead, the y value of 1. So 0, 1, and negative 4. So again, kind of you can see that this parabola here, this green parabola, is a little bit of a steeper parabola, at least if I drew it correctly. And we definitely saw that in the other picture, the actual computer-generated one. But here we can see that if we were standing at this point, then the direction vector would be, well, there's no movement in the x direction. So that's the 0 here. And then if we move 1 over in the y direction, we need to move 4 down in the z direction. So we're not moving at all in the x. If I move 1 over in the y, we need to go down by 4. So this is kind of, let me choose a different color here. I'm going to do a little bit lighter of a green just so you can really see my direction vector. All right, so now we have 2 different tangent vectors. And again, we are interested in this normal vector here. And it's supposed to be perpendicular to both of these things. It should be perpendicular to this one, and it should be also perpendicular to this red one here. And so since we have 2 vectors and we want something that's orthogonal to both of them, that's exactly what we use the cross product for. So let's go ahead and use the cross product here. I'm going to do the I, J, K, 1, 0, negative 2, 0, 1, negative 4, and take the cross product. So I always set this up just so that way I don't forget, especially that minus sign in the middle there. I tend to forget that. So let's cross off this first column and first row, and I'm going to get to 0 minus negative 2, so plus 2. Let's cross off this first row and second column. I'm going to have negative 4 minus 0. And then this first row, third column, I'm going to have 1 minus 0. And so this is going to be the vector 2, 4, 1. So the vector 2, 4, 1 is supposed to be perpendicular, right, or normal to this surface at this particular point. So this right here would be my answer. And if instead it asked for a tangent plane, right, so a tangent plane instead, so a plane that contains these 2 vectors here, and maybe I'll shade this in just so we can kind of see it a little bit better. Well, now that we have this good normal vector, we can use that in our equation for a plane, right? So the equation of the plane goes like this, right? A, x minus the x value, plus b, y minus the y value, plus c, z minus the z value equals 0. Remember that a, b, c, that's supposed to be this normal vector. So we have 2, 4, 1. That's that normal vector. And we have x minus some x point, y minus some y point, and z minus some z point equals 0. Well, we know that that special x point and y point was given to us, right? We were very interested in all of this, not at any old random x's and y's, right? But at the point 1, 1. So we know that our x special point is going to be 1, and our y special point is going to be 1. The only question really left is, what is our z special point, right? Well, it needs to be on this surface, and luckily we have an equation here that when you feed it an x value and a y value, it'll tell you what height that surface is at, what the z value is. And so if I feed x equals 1 and y equals 1 to this, I get z equals 7 minus 1 squared minus 2 times 1 squared. And so I get 7 minus 1, 5 minus another 2, no, 7 minus 1, 5. I said that so confidently. I should have just let it go and see who caught it. 7 minus 1 is 6. Minus 2 is going to be 4. So it would be z minus 4. So that right there would be an equation of the plane, the tangent plane. Okay, but since we have all this technology and whatnot, let's be paranoid and let's verify, right? So I hope you have this copied down in your paper. I'm going to switch back to my desktop where we actually have this all done with computers and whatnot here with the Monroe 3D Calc Plotter, and I would like to verify, right? And so let me go ahead and I'd like to take this off. I'm just going to show the trace point. We'll go ahead and have it. So the trace point coordinates back to 1, 1. Oops, there we go. And I just want to show that point itself, not the plane or anything like this. And let me go ahead and I would like to add a vector, right? And so the vector that we found that we think the answer is this 2, 4, 1. So I'm going to go ahead and graph the vector 2, 4, 1. And we want coming out of this point here. So, right, so this point is the point 1, 1, 4. And if I didn't do that, then it would be pretty unimpressive because it would just come out of the origin. So let's go ahead and see what it looks like. Oops, it went away. That's looking pretty good, right? That looks like a 90-degree angle there. Let's maybe look from this direction. That looks like a 90-degree angle. Yeah, so this seems like a pretty good normal vector. We could also go ahead and graph the tangent plane just to verify that. I have this, let's see if I can't get this a little bit more straight up and down like that. Let's go ahead and add to the graph a surface. And the surface that we said, it should be 2 times x minus 1 plus 4 times y minus 1 plus 1 times z minus 4 equals 0. We have hope. That does look like a nice tangent plane. Looks like it just barely skims the surface there, touching at just that point. So yeah, that looks like a good tangent plane. I'm happy with that. So let me go ahead and I want to switch back to my iPad for just one last second, kind of as we finish up here. As you, I hope, agree. I think I need to stop sharing here. Stop sharing. And try it one more time. There we go. As I hope you agree, or I suspect that you agree, this is a pretty complicated idea, right? Fixing a variable x or y to be equal to 1, allowing the other variable to kind of roam free, just continue to act as a variable in order to get these planar curves. And then we find the direction of those planar curves, and then we take the cross product, right? There's a lot of pieces to this. And that's why I wanted to go over it in this video. I'm not thinking that everyone's going to get done watching this video and just be happy, like, oh yeah, I totally get that, easy, done sort of deal, right? I'm making this because I think that, at least from my own experience, that I really started to learn things after I saw them multiple times. And so I think this is one of the most complicated things that we do in this section. And I think that having this as maybe the first time under your belt here, and then, the next time when you see it in class and when you do it in the web work homework, right, seeing this multiple times, I think has significant value. And, so when you actually have to perform this on a quiz or an exam or something, I hope that you'll do it successfully, first try sort of deal. So anyway, I hope you guys got something from this video. Even if you're not 100% happy right now, I hope that this is a good start. And yeah, let me know if you have any questions. I'll talk to you later.